Before we start though, we need to know that this guy's the calf guy, which means that he has really big calves. So I know you can't see anything under here, but he's doing it because his calves are so big.
Yeah, that's right. So today we are going to be going over Schrodinger's equations. This is just a prerequisite to future videos, in case we go over just Jefferson junctions and stuff. It is a research project I'm working on. Jefferson junctions are really quantum devices, but we are going to talk about that in another video. So quantum mechanics, Schrodinger's equation, what's that? The main idea for the invention of quantum mechanics was because a lot of the stuff that people were kind of looking at was not really explainable by classical mechanics. So stuff like wave particle duality, black body radiation, something we are going to be talking about in the future. But primarily the wave particle duality. Quantum mechanics wasn't really invented, by the way. It's kind of reverse engineered by looking at different stuff like how light really behaves, right? So looking at light itself, can I have a marker? So let's say there was this experiment called Young's double slit experiment where the apparatus kind of looks like this. You have what the fuck is this, bro? Oh my god! Always come over.
Have you where you gotta use you gotta freaking use the side.
The what?
Side.
All right. So talking about the Young's double slit experiment, right? It's got two slits. Just imagine a cardboard board, right? With two slits in it, and you have a screen right here, and you have a light source right here, right? Now let's say you're shooting a bunch of photons on this thing, or just putting some light on it. What's going to happen if we were to look at it from let's say a particle perspective? You were measuring every single particle as it was going through every single slit. You'd see there's going to be like two fringes here forming if you were to really measure it. However, if you weren't measuring it, what you'd see is like a fringe-like pattern, right? So the fringe-like pattern would kind of go like that. Now, you see, classical mechanics couldn't really explain it. You'd have to either stick to one of the theories of light either being a particle or a wave. Here's where Schrodinger's equations and quantum mechanics kind of come in, because it kind of deals with probability and the behavior of light. One of the other things classical mechanics cannot explain is the existence of an atom, right? Because, you see, there was this guy, Rutherford, who came up with the idea of electron orbiting the actual nucleus, right? However, according to classical mechanics, the electron itself should lose a lot of energy and, end up sticking to the nucleus itself. So this guy named Heisenberg or Bohr, they came up with the they said that it doesn't really work like that. We have energy levels and stuff, and electrons, they just end up existing in these energy zones, and they don't really stick to the nucleus because, there's no energy loss. That goes into hydrogen spectrum, which we are also going to be discussing in the future. So yeah, Schrodinger's equation. What is Schrodinger's equation? It's literally just an equation that looks like a wave. It's a partial differential equation. Kind of looks like someone pulled it out of their ass. It's got a long ass derivation, but you don't really need to worry about it. Okay? Yeah. Don't scare them. No.
Okay, well before you continue on, okay, well you erased it. You erased my question.
No.
Basically,
Uh-huh.
so my two questions is one, which should be really easy for you to answer for me. I don't understand. Can you explain like the main principle as to, is it just the atom that separates quantum mechanics and classical mechanics?
Mhm.
What's the difference? And then as to you're showing two dots, for example, that creates a wave. Can you explain so the wave is what it'll look like if it's unmeasured, right? Is that what you were saying?
Can you phrase that better?
Yeah, you were saying. I guess that's a question I have then. Why does it end up as a wave? Why does the why does where these two electrons go not go into like two singular parts, singular areas instead of why does it create a wave that
You see, that's a great question because that's one of the things quantum mechanics kind of answers. You know, it's really counterintuitive. It's not intuitive at all. Well, unlike classical mechanics, which is super intuitive, you just have to know. It's just an established fact that it just behaves like that, and you just have to live with it, sort of, because like it's.
have they done anything
it's
to
just
try to
what
figure
happens.
out if there's a way by which they know where that electron's going or that you're saying photons, right?
Mm-hmm. Yeah, photons.
Yeah, like did they do any
Yeah.
tests or anything like that to
Yeah. We are gonna be going over that in a bit.
Okay.
But to answer your question, you can just think of photons as these wave packets, and
Yeah.
they are from a particle perspective, right? They're just a packet with energy in it, and those energies have certain wavelength and stuff. I know this all kind of sounds nutty when you think about it, but as we study the Schrodinger's equation and the rest of the stuff,
Yeah.
it would make sense. But going on over Schrodinger's, also to answer one of your other questions,
Classical versus spin.
yeah, classical. Why does classical mechanics fail? It just so happens that it fails because and there's
Just like people in life.
yeah. It just people saw that a lot of the stuff that was happening on a minute scale didn't quite line up with what classical mechanics was supposed to make people understand. So they really had to reverse engineer what was going on,
Yeah.
and they said that it's interesting because Einstein thought that quantum mechanics was a bunch of bullshit, so he didn't really give a fuck about it. But yeah, so
So I guess he's not that smart after all.
I wouldn't say that. I mean, Newton went into theology and stuff after the invention of fucking calculus, so I wouldn't say that. But Schrodinger's equation, it looks fucking scary. By the way, it is scary. But we are gonna make it less scary as we move on. There's a statistical interpretation of what the Schrodinger's equation is. Let's just say the existence of particle itself can be given in terms of probability, right? So you can see this function right here. Yeah, this is a function dependent on position and time. This is one-dimensional because we are only going to be talking about the x-axis. We are not going to care about x, y, y or z. We're going to think about that in the future. We're going to convert that in spherical coordinates and stuff. But if you take this function right here and you square it, what you get is the probability, right? Probability of what? Of a particle's existence in a certain region, right? So if I were to integrate it, do you know what
Integral is.
Yeah. Do you know what that is?
Yeah.
Yeah. So if you were to integrate the particle's existence or the probability from a certain region A to B, I'm referencing to this graph, by the way, which is a plot of probability versus position. You can see if we were to integrate it from A to B, you'd get the probability of finding the particle itself in this certain region right here. All right. Now, there are three. By the way, do you have any questions so far?
Yes. So basically, back to your point, just make sure I'm following.
Mm-hmm.
Probability is because it's not exact as to where this particle is going, but they're just finding ideas where it probably is going.
Yep.
My second question is, so why are you squaring? Yeah, why are you squaring whatever the fuck this thing is? What is this again?
That's the wave function or psi.
Yeah. So why are you squaring psi?
That's also a great question. Even Schrodinger had no idea why the fuck he would do it. He was doing that. So it just so happens to be if you square it, you get the probability. All right. I mean, I'm pretty sure there's like a long ass, rigorous
Explanation.
experimental explanation to it, which I don't think I can afford because I'm not rich. But yeah, it just so happens to be that the square of the wave function itself is the probability of finding a particle between a certain region. Statistical interpretation. There's three statistical interpretations of quantum mechanics, which not only kind of disturb physicists themselves, but also philosophers. There's the realistic, orthodox, and agnostic. Realist people say that particle was at a particular point. If the most probable point was like C or something, or D or E or F, right? We would say that the particle exists. But you can see this. Even Einstein kind of agreed to this and advocated for this statistical interpretation of quantum mechanics. But this is kind of stupid. Also, then there's orthodox, which is the particle wasn't really anywhere. Kind of stupid. Fucking stupid. I mean,
yeah.
It's not really anywhere in terms of whether you're measuring it or not. So the first two are stupid in the sense that you're not measuring it at all. I mean, if you're measuring it, only then would you be able to study physics. If you're just going for realist or orthodox, well, you're not really studying physics. You're just studying metaphysics or something like that. Then comes the agnostic. As pitiful as it sounds, refuse to answer. It's really not, because, well, you haven't measured anything, so you don't know where it exists. So you might as well just refuse to answer than be probably wrong or probably right. All right, so that's pretty much the basis of why quantum mechanics kind of exists and the statistical interpretation of quantum mechanics. Do you have any questions?
I'm assuming you're agnostic.
Well, I have to be agnostic, otherwise I won't be able to study physics.
Yeah. Well, are they still trying to figure out as to whether or not there is have they given up trying, or is there even a reason as to find the exact point of electron, or is it just? I did hear something that's just it's just impossible, right?
It's just impossible for what?
To find an exact point of where an electron will end, right?
You're just basically gambling at that point. Why would you do that?
Okay.
You would rather have an exact probability
rather than
measure of where the electron is likely to end up, instead of unless you are actually measuring it, than to actually make guess or gamble. Imagine having fucking quantum gambling, bro. It would be so cool.
Bet you don't know where this next electron would go. I do.
Yeah. Okay. But if we can go over probabilities and stuff in another video, but it's a crash course. It would be super simple. I mean, it would make quantum mechanics much more easier to understand. However, this just gives you an overview of what quantum mechanics really is. Moving on to normalization of function. This is just for the I would say this is just for the sake of computation for most of the problems, but it follows a pretty trivial equation right here. It's negative infinity to positive infinity integral of psi function square dx equals 1. Which just says that the particle does exist somewhere, right? From the bounds negative infinity to positive infinity, particle does exist somewhere. So you're not questioning its existence at all. You're just saying that, oh, it exists, but where? Negative infinity to positive infinity. So we are saying that it does exist. But does it stay normalized for every single t? What I mean by that is, does the normalization change at all?
Yeah.
Is the normalization the established truth that the particle itself exists? Does it change with time, right? We're going to prove it. So here's the proof. Looks kind of rigorous, but really what it is you have the actual normalized function right here, and you differentiate it in terms of time. What we are trying to prove is that it doesn't change. So we're saying that, the differentiation of this function right here should result into 0, saying that, it doesn't change with time. Can you say, well, just tell me, what is differentiation? What does it do?
I don't know. It's like find the derivative of
Yeah,
an
well, what
integral.
is a derivative in terms of intuition? Like
I freaking know. To solve a derivative, do I know what a derivative is? I don't know something.
change of something.
Something. Well, change of the power,
something,
right?
yeah.
But I don't know what the
No,
use
change
of.
of something with time. So if you were to know a particle's position, let's say a particle is at position x on a certain line, right?
Yeah.
It's at a position x naught, let's say, at a certain time t equals t naught, right? However, it's at a certain point x1 at t equals t1, right?
Yeah.
How would you find the velocity? Velocity is change in distance divided by change in time, right?
Okay.
Now, let's do something.
Yeah.
We can decrease this distance, right? We are gonna make it so fucking small that it nearly looks like a point, right? So make the distance small, dx. Let's say this measure is dx, right?
Okay.
And this is t, and let's say this was x naught, and this is x1, and the time it takes to travel from x naught to x1 is delta t, or dt, right? What would the velocity be? It would be distance over time, which is dx over dt, right? What does this tell you? Well, velocity itself is the change in position with time. So, when you're taking derivative of something, what you're really doing is you're asking, well, what happens with the change in terms of a certain other variable, right?
Mm-hmm.
That's what happens when you're taking derivative. That's what you are answering, all right? So here what we are trying to prove is that with the change in time, the normalization itself doesn't change. So, can you answer? Like, what would happen if I mean, what am I trying to prove here? Can you tell me? Like,
Oh.
yeah.
I don't know. Okay. Well.
Trying to prove.
So.
Sure. Go ahead.
Well, I'm just trying to connect it all together, right? And so, well, we know that with an electron or photon or whatever, we don't know as to where it's going to go, but we know it's going to be on the graph, right? So
Yes.
we know that it's going to be a wave. And so as we create this wave, it goes up, down, whatnot. And this is as long as it goes through negative infinity and positive infinity. But maybe we can find the probability of where it will go, whether it's going to maybe rise or fall, based on the derivative that helps us as we go along the x-axis, or as we go in what velocity along with time, we can kind of I don't know. I'm just well, because okay, so you're saying that x over t, so that's going to be what is velocity over time, right?
X,
No, or
X is position.
Okay, the position over time.
Velocity
So we
is
can
changing
we can
position
find
over
along the time maybe the positioning of the electron.
You're close.
Okay, so
So,
it wasn't as far as I thought.
Going back to normalization, this is just for the sake of computation. This thing is an established truth, right?
Okay.
What we are asking is, would this truth change with time? Because this is for the position. You can see this is for the position. We are integrating it in terms of position. Right?
Yeah.
Would this truth change if we were to take another measurement at, let's say this measurement was taken at t equals t1, right?
Yeah.
Would this change? Would the normalization change at all if we were to take it at t equals t2 or t equals t3, right? The answer is no. The normalization would almost always be 1. If you were to like integrate this thing, negative infinity to positive infinity in terms of position, you'd always get 1. It would not change with time. To prove this, we are going to use the derivative of this function in terms of time.
What does the one mean again? Can you remind me?
1 is the probability. So
Of it existing, right?
Yep. So when I say 1 always corresponds to 100%. Like, the particle 100% exists.
Okay.
If I were to say 0.5, it would mean 50%. The existence of the particle in that particular region is 50%. If I were to say 0.75, what would it mean?
75%.
75%.
So there's always 100% of the time that electron exists, and so you're trying to prove on whether or not whether you go through, you progress forward
With
along,
time.
or backwards, so that will the electron ever not exist or become 50 or 75%? And what you came to the conclusion is that it's 100% factual that the electron will always exist along
Negative infinity, positive infinity.
Okay, and so
How did I do it?
no. Then does the proof help find like the exact point? Because I'm seeing the graph here, right, and it goes down.
Proof
and up.
is the proof that this exists.
Okay, so then where's the proof as to whether or not? Because it seems like the electron goes in bunches, right? Kind of like with the graph. Like with the graph rises and goes down, it has specific.
This is probability.
Yeah, there's a probability.
This is just an arbitrary graph. This is not something that universally exists. By the way, it's just a graph that I'm using it as an example.
So, but there's a probability of it landing in one spot, right? Like an area of a spot.
Yeah.
So then, what are you doing to find the probability of where it will go with it? You know what I mean?
Can you repeat that?
What is the probability? Like, as you were showing where that electron was going up or down.
Up or down?
Up or down. Like you had two like little doors. You know what I mean?
Oh, don't think about that for now. Just think about like an arbitrary.
Okay, so electron just exists. That's what you're just trying to prove.
Exists.
So is it the probability that you explain next time, where it's?
Yep.
Okay.
That would be something we will go in over next time.
Clickbaiting me, man. You're giving me all this
Oh, come on. Right? I'm not doing shit.
I mean-
So this thing is just an arbitrary function. So I mean, you don't really need to worry about it where it came from or anything. But it's just an arbitrary function of the probability of an electron existing in certain regions. So A to B in this graph, it just tells you what would be its probability on x equals, let's say x equals fucking D or something, right? And that would be some value of psi squared, which is the probability of it existing. But yeah, so what I was trying to prove there is would the normalization change at all if I were to take different measurements with time? So the answer is no, because if you differentiate it, you end up getting 0. So 0 means there's no change in time, so you can always trust normalizing it in terms of x, negative infinity to positive infinity, right? Moving on. Okay.
Professor Avi.
Yeah. Moving on. We got momentum, right? We're gonna start with
God damn, man. This ain't short people friendly, bro. We need to get a camera.
Yeah, momentum. So, as you can see, I've written here a not so scary character, x, with brackets. And the brackets means you are trying to find the expectation value of something. How you find the expectation value is you basically just multiply the wave function square, which is the probability, with x. Again, we are going to be going over this stuff in another video and probabilities and stuff if you want to watch that. But negative infinity to positive infinity, you integrate it, you multiply the probability with x, and well, that's how you get the expectation value. Then as we were talking about momentum, right? This is not momentum. This is the expectation value. However, if you wanted to find the velocity or the expectation value of the velocity, what you would do is differentiate the expectation value of the position of a particle in terms of t, and you'd end up getting this thing right here, which is also proven by some rigorous proof. We're not going to go over that because it's hella useless. You're not going to be using that anywhere. But you just end up getting the velocity. However, it's customary for us to use the momentum itself because, well, momentum is way much more useful for finding kinetic energy or anything, or angular momentum, let's say, right? So we multiply the entire thing with mass, and you end up getting this, which is negative I h bar integral of psi star, which is, by the way, the imaginary conjugate of psi, the wave function. As you can see, this wave function is imaginary because it's got I in it. I it being square root of -1, and h bar being the Planck's constant, right? Let's go back to what the expectation value is. Expectation value does not mean if you were to do the same measurements again and again, you'd end up getting this particular value. It rather means that if you were to do same measurements, given that they were all initially in the same state, psi, you'd end up getting this number, which is the expectation value. Right? Does that make sense?
Read it one more time.
So let's say if you were to have particle 1, P1, P2, P3, P4, and so on, right?
Yeah.
And they were all initially in the state psi.
Yeah.
Psi here is a wave function, by the way. We can also call it a state of the particle. And if you were to keep time constant, right? T equals T naught or something, right? You weren't changing it with the time, right? Because remember, Schrodinger's equation, Schrodinger's function or psi or the wave function is also time dependent. We're not dealing with time independent Schrodinger's equation yet. That's going to be the next video. But if we were to measure it at some particular time T naught, and we were to measure the probability not the probability, the expectation value of a particle existing at a particular position, right? That's what the expectation value is. You'd get at t equals t naught, the expectation value would be x in brackets. So in probability sense, this would be the mean of all the values. So yeah. This would be the mean of all the measurements taken by P1, P2, P3, and P4. Moving on. Do you have any questions, by the way?
No.
No,
I don't. I I seriously don't. I don't.
Does it make sense though?
Kinda. I'm like, I have the understanding of it, but if you ask me like to explain it myself, then I'd be like, ugh.
Means you didn't understand it. So, what I mean by a particle being in the same state, did you understand that?
Mm-hmm.
What does that mean? Schrodinger's equation changes with time, right?
Yeah, so that's the part I was a bit confused. Equation, so, you said there was independent, right? Independent Schrodinger, whatever.
Time independent Schrodinger's equation. Yeah.
Okay. But we're at independent right now.
Yeah.
Okay.
Time dependent Schrodinger's equation. We are on that stuff right now. Time independent stuff is more useful. However, we are just going to be going over time independent to get like an intuition of what it really is. And like get some basics clear. But yeah. So when they're in the same state, what I mean by that is they are let's say psi starts with a certain value c.
Yeah.
Right? That's a state C right there, and all of them have the value C on it, right?
Okay.
So psi P1 is C, psi P2 is C, psi P3 is also C, and so on, right? When I am taking the expectation value, I just mean I'm taking the mean of all the measurements.
Okay.
Of all these particles.
Yeah.
Right here. Right? So, how do you, could you tell me how do you take the mean of something or the average of something?
I don't know.
So, for you to take the average of something, you just multiply the frequency, right?
Yeah.
The frequency of something happening, multiply by the actual number itself, right? divided by the total number of outcomes, or the total number of people, or the total number of particles in this case,
Okay.
right? Which is going to be ng divided by n, right? And you sum that up in the numerator, right?
Okay.
Where j goes from 0 to infinity, right? And you then see that nj over n right here
Mm-hmm.
is also probability
Okay.
of the event j happening, right?
Mm-hmm.
From all the events n. So what you can write it as is j times p of j from 0 to infinity. This is also the same thing as saying the expectation value of j.
Okay.
That makes sense?
Yeah.
So, the expectation value of a position of a particle can be determined by taking the mean of all the measurements, or probability of a measurement, multiplying it by the state, which is x, and integrating it or summing it from 0 to infinity.
Okay.
Does that make sense?
That makes sense. Yeah.
Cool. Fuck, it's fucking hot. Okay. Now, going over the expectation value of a velocity, you just differentiate it in terms of t. Basic physics. Well, dx over dt is velocity, right?
Mm-hmm.
You know that, right?
Yeah.
So,
Based on that.
yeah. It's the same thing for expectation value for velocity. You just differentiate it in terms of time, and you end up getting the expectation value for velocity, which is this thing right here. How do you find momentum? Momentum is P's momentum is mass times velocity, right?
The mass is what? Is that Newton?
Mass is just mass. Just mass. Just mass.
No?
Mass of anything. It's nothing exotic, alright? It's just mass.
Yeah, no. I was thinking of
yeah.
freaking goddamn momentum.
Bro, momentum in this case is P, so that we don't confuse ourselves, alright? Mass is M, V is velocity. Mass times velocity is momentum, right?
Okay.
However, in this case, we are dealing with expectation value, so we are just going to be using the expectation value for velocity, right?
Okay.
Fuck. Right?
Okay.
You can also write the expectation velocity as m times d, expectation value of x, or position, divided by dt, right?
Mm-hmm.
And by some rigorous proof, which we're not going to go over yet, dx over dt just so happens to be m times, dx over dt just so happens to be negative iota h bar over m psi star del psi over del x times dx whole integral, which is, it's just some rigorous proof. We're not going to go over that. It's fucking ass. But, yeah. Up negative I h bar over.
Guys, just know if it's fucking ass, then just don't do it.
Yeah.
Math teacher says it, it's fucking ass.
No, just fucking plug in the values when it comes up, you know? Just don't go in the exam just trying to fucking prove the existence of quantum mechanics. That's not, I don't think that's what the professors are going to ask you for. But, yeah. Also, that's not something we're going to be requiring for understanding Josephson junctions or anything. But yeah, this is momentum in quantum mechanics. This is what it looks like. Fucking abomination.
This looks ugly as shit, man.
This is what I'm talking about. This was in classical mechanics, and this is what you get in quantum mechanics.
Yeah.
You will come to realize momentum isn't actually a value. It's actually an operator, which means momentum is just written as m times negative I h bar over m.
Operator, what do you mean by that?
Operator, like plus, minus, divide, multiply.
Oh,
stuff.
okay.
Yeah. No operators.
Operations.
Yeah. Those are operations.
I know. Yeah, I was just...
Similar to that. You're just...
let's do some...
If you were to, like...
We utilize this operator.
Yeah.
It's all multiply.
Yeah. Or, like, it's kind of like putting something into a function. Let's say f of x is ax squared plus bx plus c, right? And you were to put x equals 1.
Yeah.
Then you'd get f of 1 as
Yeah.
A plus B plus C. Operators are just functions for functions, if that makes sense.
That makes sense. Yeah.
Yeah, you just put in function inside of an operator, and it gives you like a shittier function. That's what it does. I could make a diagram for it. So almost like functions kind of look like this, right? You have an input variable, and it gives you an output variable.
Ah, yeah, I've seen those.
Right?
Yeah.
An operator, however, it takes in a function, and it gives out another function.
Okay.
Right?
Makes sense.
Whatever. But this is an operator, which means it depends on psi. So, actually, the momentum just kind of looks like negative I h bar d over dx.
Yeah.
You see how there's like no variable right here? It's just empty.
Mm-hmm.
So you gotta feed it a function.
And then there's okay.
Yeah. So to find the expectation value of any anything pretty much that has momentum in it. Let's say you have kinetic energy K or T or something. What's kinetic energy in terms of momentum? P squared over 2m. Right?
I don't know. Listen to you, Professor Avi.
So P squared over 2m divided by 2mv. Just have negative I h bar. I hate my life. Negative I h bar. Del over del x. Right? And you just have the square. And this is the operator for kinetic energy. To find its expectation value, you feed it a function, and it gives you like the actual kinetic energy of a particle. Yeah, that's the basis for quantum mechanics for you. Moving on to this stuff, uncertainty principle. This has got to be simpler than whatever the fuck we were going on before that. But what it says here is, let's say you have a man making waves on a string, right? Perpetually. You'll see the string would go kind of like whoop, 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 whoop.
With those sounds.
No, not
it has to come with those sounds.
It's just for fucking visualization, bro. And let's say there's a guy who comes up and he asks, "Oh, can you tell me where the wave can exist?" You know?
Yeah.
And then
he's like, "It's whoop."
No, not. We are not gonna look at this one.
It's whoop 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 whoop.
Yeah,
like see that's where it exists. That answers.
But if a guy comes up and you're doing this shit on the rope, and he asks, "Oh, can you tell me where the wave exists on the rope?"
Yeah.
What would you think? The guy's a fucking asshole. Like, how can you tell where it exists? I mean, you can certainly tell the span of the wave, right? You can tell what the wavelength of this thing is. You can tell what the amplitude of this thing is because it's a wave, right?
And that's where it's uncertainty principle. You don't know where it is.
No, I mean like.
But you don't know the exact point.
You don't know.
It's just one, so it's just.
Yeah, because it exists everywhere.
Negative.
However, if you were to make like just a pulse on the wave, right? A pulse, right? Which kind of looks like that.
Yeah.
A boner in a pan. But.
A boner in a what?
Nothing.
In a pen?
In a pant.
In a pant?
Yeah.
What's a pant? Oh,
same stuff you're wearing right now.
I don't think.
What do you want me to say? Trousers, bro?
Los pantalones, something like that.
Oh my god.
Those pants. It's pants. It's not pant. you got two freaking multiple.
Nah, I just say pant. I just wear a single.
Well, what are you wearing? I'm wearing a shirt and I'm wearing a pant.
I'm just wearing like a singular pant on one of my buttons.
The other one has shorts on, so
yeah,
short and pant.
Short and pant is what I'm wearing. Yeah, that's not what I'm wearing, by the way. No, do not pan the camera over there. But if you were to ask the position of a wave on this one right here, it would make more sense because like now you know the position. However, if I were to ask, oh, what's the wavelength of this thing? Would you be able to tell? I mean, like, sure, if you were to like expand this more, you'd be able to tell, but you can't, you know, because it's not a wave. It's a fucking pulse. You can only tell the position and like the amplitude of this thing. So this is where the de Broglie formula comes in. De Broglie formula just tells you the de Broglie wavelength of anything. It kind of sounds like jargon. It just tells you the wavelength of a particle. So P equals h over lambda. P being momentum, h being Planck's constant divided by wavelength lambda, which is also equals 2 pi h bar. H bar is one of the fancy ways of writing the Planck's constant. So you can just say h equals 2 pi h bar, right? So moving on to the uncertainty principle, or Heisenberg's uncertainty principle, it just says that the standard deviation in x and standard deviation in momentum, when multiplied together, should be greater than or equals to Planck's constant divided by 2. Why? We're gonna go over that in some other video because it consists really rigorous proofs. So yeah, it'll take like half an hour or something, but yeah. Jeez. Any questions so far?
No. Yeah, it's like all I have to say is no, and you know.
Fair.
But yeah, I don't have questions. You know?
That's right.
Like questions as to like the idea of it. Of course, if you have me, if you erase all the whiteboard and like do it, like fuck.
You're a
be like, hey, luckily I took a picture beforehand.
Yeah.
But no, you're explaining the idea of it pretty.
In the next video, however, we're going to be going over.
As you can tell, this next video is going to have a lot of shit because.
No, it's not going to have a lot of shit. It's just going to be super fucking friendly. It's just that. Can you not imagine a room full of 14 people, bro? Like it's.
Seems like a lot of people.
Still 14 people. And if 14 is like 1, which tells you the frequency of 14 people existing, which is how many people aged 14, how many people of age 14 exist in that room, which is 1. This is just data. I'm making up data here, by the way. So
yeah, I can tell.
So and of 14, how many people aged 14 in the room? 1. How many people aged 15 in the room? 1. 16, 3, 22, 2, 24, 2, 25, 5, 17, 0, because we already reached the limit. But then you have stuff like total number of people in the room. How are you going to find total number of people in the room? And just sum up all the ages, the number of people of all ages from 0 to infinity. Well, infinity doesn't really make sense because I mean, like, it kind of breaks you, but if you really think about it, it's not that rigorous. You're just adding up all the numbers and you just end up getting 14, right? Right?
Yeah. It would have been funny if, like, it didn't add up to 14. You had that wrong. It's like 2, 3.
No, that's quantum mechanics. But and essentially in quantum mechanics, you just have like 5 questions you're primarily answering, which is probability that a person's age you pick at random is 15, or most probable age, or median age, mean age. What is the average number of what is the average of squares of ages, which does sound a little complex, but it's really not. It's just
you can see
J
there
squared.
with all that, it's not
just
complex at all.
Just the mean of J squared, right? It's not that complicated at all. But yeah, we are certainly going to be going over more examples, statistical examples in the next video, which is going to be joining us, which is going to be joining quantum mechanics. And it would make more sense. Quantum mechanics would make more sense in that case. Statistical quantum mechanics, but mathematical stuff, I don't know about that.
We'll see.
Yeah, we'll see.
We'll see.
Yeah.
Okay. Any last thing to say to the people that are watching this still? By the way, this is your next physics teacher, so
No, I'm not. I'm fucking not. I'm a researcher, bro.